Hey class, today we're going to talk about theorems about roots of polynomial equations, which is found in section 5-5, part 2 of your book. Our objective is to use the conjugate root theorem and Descartes' rule of signs. Alright, so in example 3, we're going to use the conjugate root theorem to identify other roots. This actually is fairly simple. The one thing that you need to understand is that the conjugate root theorem basically talks about like if you have one root, you're going to have another. For example, that plus or minus part that we deal with quite often. So with complex numbers, okay, if you have a plus bi, you're going to also have a minus bi. And then when you are dealing with irrational numbers, so that's basically like your radicals, right? If I have a plus the square root of b, then I'm also going to have a minus the square root of b. And that's just because of that simple plus or minus that we have to deal with. So it goes on to say, and I apologize for this error, it's supposed to say quartic. Anyways, a quartic polynomial p of x has rational coefficients. If the roots listed below are the polynomial function, what are the other or the two other roots? And to be honest, this didn't even have to tell us what are the two other roots. It just could have said what are the other roots, simply because it's telling you that it's quartic. So that means you're going to have 4 roots. Okay, if you know that one of them is the square root of 2, well, then that kind of matches with that one. So its pair is going to be negative square root of 2. Okay. Then it goes on to tell you 1 plus I is a root. So again, that matches with this one. So its pair is going to be 1 minus I. Okay. So we're done. That's all you have to do. Let's do that again on our try. So they tell you it's a cubic polynomial, so we know that means it needs to have 3 roots. Okay. They tell you what 2 of them are. You really just need to find the third. So if you have 3 minus 2i, its pair is 3 plus 2i. And then 5 halves doesn't have a match because it's a real number. All right, on example 4, now we're going to use conjugates to construct a polynomial. So first it tells you that it's a cubic polynomial, so that means it's going to have 3 roots. Now, after we know that it has 3 roots, okay, we need to find those 3 roots and multiply them together to get our polynomial. So our first root is negative 4. It's a real number, so we're fine. The next root is 2i, but its pair must be negative 2i. Now that we have the roots, we need to come up with the factors. Remember, roots are the same thing as zeros. So if the answer is negative 4, what was the factor that made the answer negative 4? That one would be x plus 4. Same thing for 2i. In order for that to be a function, it would have been, and as far as a plus bi, right, that's really what that is, a plus bi. So that's x plus 2i, and the other one is x minus 2i. So these two with the imaginary numbers aren't necessarily what makes it 0. We're just putting them in their form. All right, so if we continue, we need to multiply. So I'm going to leave x plus 4 alone, but I'm going to multiply these two here. So to do that, I'm going to use my box just so I can show you. So x and 2i, x and negative 2i do not get thrown off by the fact that you have more than one variable. Okay, this becomes x squared. This becomes negative 2ix. This becomes positive 2ix. And below that is negative 4i squared. Okay, the diagonal cancels there. And we also know that negative 4i squared is really the same thing as 4. So really this is still x plus 4, but the other one is x squared plus 4. Now if we want to do another box to finish that, we can. So if we do that, x and 4, x squared and 4. So it becomes x cubed, 4x, 4x squared, and 16. Put that in standard form, and your final answer will be x cubed plus 4x squared plus 4x plus 16. We are done. All right, let's go ahead and do the try. All right, so the pair that matches for 2 minus 3i is going to be 2 plus 3i. Okay, so the roots here, now you have to be careful here because what you're trying to do is figure out what the root is going to be if I set that, like these are my answers. So 2 plus 3i is my answer. So how did I get that as my answer? In order for 2 to be positive, it would have to be x minus 2 plus 3i. And again, for the next 2 to be positive, it has to be x minus 2 minus 3i. And then the last two are fairly simple. To get 8, I'd have x minus 8. And to get 2, I'd have x minus 2. Okay, these two multiplied together are fairly simple. You'll have x squared minus 10x plus 16. That's not what we have to really worry about. We need to worry about this center part here. So let's deal with that. This is going to be a 3 by 3. There are 3 terms. So we have x, negative 2, 3i. X, negative 2, negative 3i. Okay, this is going to give us x squared, negative 2x, negative 3ix. Okay, keep going. That's negative 2x. 4, 6i. Next is 3ix, negative 6i, and negative 9i squared. Okay, here our diagonals are going to be like terms. By the way, that negative 9i squared, we can replace that with just regular 9. So if we keep going, the like terms, I see my highest power, and that's a negative 3ix. And my highest power is going to be x squared. What I notice next is that my ix's are gone and my i's are gone. So I'm left with, as far as the x variable, that's negative 2x and negative 2x, which is negative 4x. And then I have a 4 and a 9 that can be combined, and I get 13. So now I need to multiply those two boxes together. So those two boxes, again, is a 3 by 3. I have x squared, negative 4x, and 13. The other one is x squared, negative 10x, and 16. So if I multiply that, I'm going to get x to the 4th, negative 10x cubed, 16x squared. The next row I get, or next column I get negative 4x cubed, 40x squared, negative, let's see, 16 times 4. We're going to get negative 64x. All right, then you have 13x squared, 130x, and then 16 times 13 is going to be 208. Oops, 208. 08. All right, so our final answer now, be sure that you combine like terms, right? Because those are like terms. And then we have these as like terms, and then we also have the x's again. Okay, our polynomial, and this is taking a lot of work. So our polynomial is x to the 4th. The cubes are going to give us negative 14. And let me use a whole different color. Probably should have just did that the first time. All right, sorry, here we go. Our final answer is x to the 4th. The cubes are going to give us negative 14x cubed. The squares are going to give us 16 plus 40 plus 13, which is going to be 69x squared. Our x's are negative 64 and negative 130, which is going to give us negative 194x. And last, I need to add 208 to that. And that is our final answer. Now, the most difficult part of this problem was dealing with the fact that that was 2 plus 3i and 2 minus 3i, and then writing the correct roots. If you did not write the correct roots, then you would get it incorrect. Now, again, the whole reason I chose a negative here for both of them is because my 2 was positive. It had nothing to do with the plus 3i and minus 3i. It had everything to do with 2. In order for it to be positive 2, then I would have to have subtracted x from, what these complex numbers are. Okay? That was a lot. So let's do the next one. Now we're talking about the Descartes rule of signs. And it's a lot to explain based off of this slide. So if I kind of go through it, just kind of go with me. So if you look at the first bullet, it says, first of all, that the polynomial has to be in standard form. Okay, we know that. Now, after it's in standard form, so the number of positive real roots is going to be either equal to the number of sign changes between consecutive coefficients, or is less than that by an even number. Okay, and then the number of negative real roots is either equal to the number of sign changes between consecutive integers or consecutive coefficients when x is 0, or excuse me, when you substitute in negative x, or is less than that by an even number. Now here's the deal. I know that sounds really confusing, so let me show you what that means in example 5. So in example 5, to be able to test the positive roots, okay, to be able to test the positive roots, and I don't want to write p of x, I want to write positive. To test something that's positive, you have to use regular p of x. So p of x will equal x cubed minus x squared plus 1. Okay, everything here is in standard form. And I'm using the regular function that was given to us for p of x. Okay, now that I've got that, I need to check my sign changes. Okay, from positive x cubed to negative x, from negative x squared, there's a sign change. Okay, it went from positive to negative. And then from negative x squared to positive 1, it changes again. So in this case, there are 2 sign changes. Okay, so here's the deal. You can either have 2 roots or you can have 0 roots. And I would know that it's 0 roots because it would be 2 minus an even number. That even number is going to be 2. So it can either be 2 roots or 0 roots. Okay, and we'll use the calculator to verify in just a moment. Okay, so when you type that into your calculator, go to y equals and type in x cubed minus x squared plus 1. Remember, roots are the same thing as 0, so we're checking to see where it crosses the x-axis. And you will notice that the amount of times that it crosses the x-axis as far as positive roots is 0. It is not going to cross the positive roots more than 0 times. Basically, it's never going to do it. Okay. All right. Now let's check for our negative. To be able to figure out how many negative roots there are, okay, we will, instead of using positive x, we're going to use negative x. So that's p of negative x would be negative x cubed minus negative x squared plus 1. We just need to deal with sign changes or integer rules first. So a negative cubed is still going to be negative x. So this is still negative x cubed minus a negative x squared is going to be positive x. So this becomes positive x squared, and you still have plus 1. So let's count the amount of sign changes. There isn't a sign change here, right? Because a negative to a negative is still the same. And then a negative to a positive, that changes once. So there's 1 sign change. So in other words, there is, sorry, and I should have written at the top, this is 1 positive root or 0 positive roots, and this one is 1 negative root. And again, this can all be verified on a calculator. Okay, let's do our next one as a try. All right, so again, to find the amount of positive roots, We just check the sign changes between the function or between the terms. So we have p of x equal to 2x to the fourth minus x cubed plus 3x squared minus 1 equals 0, or not equals 0. It's already equal to p of x. There are, between 2x to the fourth and negative x cubed, there's a sign change. There's also a sign change between negative x cubed and 3x squared. And there's also another sign change here. So really, this one is either going to be 3 roots, 3 positive roots, or if I subtract an even number such as 2, it would be 1. Okay? Now, we would verify based on the calculator how many positive roots there are, and what you're going to realize is that there is 1 positive root. Only 1. All right, to check the negative roots, that's p of negative x. So that'd be 2 times negative x to the fourth minus negative x cubed plus 3 times negative x, I missed a number, 3 times negative x squared minus 1. Okay, we got to deal with the integers first. So a negative to the fourth power is going to be even still. So this is 2x to the fourth. A negative to an odd power is negative, but I also have a negative right here. So a double negative is going to make that positive x cubed. Okay, a negative squared is positive, so it's still going to be positive 3x squared, and then we have minus 1. So no sign change there, no sign change there. There's 1 sign change here, so there is 1 negative root. And guys, we are done. If you guys have any questions, please be sure to come check, come check in with me for tutoring.